Sample problem. A disk of radius r has a uniform charge density sigma with units of coulomb meter squared. Find the electric potential at point P on the axis passing through the center of the disk. We can see from the figure. Some of the parameters are seen and calculated here, like the length d. We imagine that we take small circles with a charge of dq. Here we take a small segment dq of the disk and determine the electric field at point P by the segment. We see that the distance d is just the Pythagorean equation, and we notice that as we evaluate the charged disk the distance d changes or the r varies. Examining the equation for d, we see that the distance x along the horizontal remains and only the r distance changes. Here we divide the disk into infinitesimal segments of rings with dr as shown here. This small segment has a small charge we call as dq, and it exerts a field on a point P. Now if we consider a point on the segment that is identical to the previous one but positioned on the opposite side, we have a cancellation of the electric field along the y-axis. So we see that the net electric field is solely due to the x-axis. We write the net electric field as equation A. We consider now the integral function, which we write now as equation 7. We modify this function to incorporate the parameters of a charged disk as shown in equation B. Expanding further the integral, and we now left with the function with d distance as shown in equation C. The cosine function can be calculated by examining the figure as shown here in equation D. Substituting this back to the equation, we have function E. We note that dq is a representative of the disk, so we consider the surface charge density function as shown by equation F. The surface charge density is evaluated on the total radius of the disk 0 to r. We also substitute the value of the dq as a function of the surface density as shown by equation F. So equation E can be written as equation G. We also factor out the surface charge density and further simplify it with incorporation of the surface charge density as the total charge Q and the total area of the disk. We then have the function h, where we need to solve the integral function. Considering the integral function and solving it, we also evaluate it from the total radius from 0 to r as shown in equation I. Finally, we have an expression for the integral function as shown in equation J. We then substitute back the solution for the integral back to our equation for the net electric field. So the electric field exerted on a point P is given by equation K.